Uh-huh. Uh-huh. Test. There's my condenser mic. There we go. All right, there we go. How is everybody today? Oh, I'm just gonna shut off the baby monitor. Give me a second. Here. Oy. There we go. That's just the thing you don't need to listen to, you know? Let's see. Daniel is dead. Long live the Daniel. I am not sick. Yes, well, yeah. I am. I am sick because I have in my household a 11-month-old who, you know, little kids are great. I love having a little guy running around, but holy smokes, is he a germ factory? Like, honestly. And you know, it's like, I get that he's a baby, and one of the things he needs to grow and develop is his immune system. But holy smoke, could you just lay off the licking the shopping cart handles? Like, it just everything he sees, he has to put it in his mouth. It's amazing that we all start off life in such a manner and live to tell the tale. But yeah, you know, I was actually a lot worse this morning than I am right now, so I'll probably make it through the lecture without any great fuss. But thank you very much, everybody who is joining us concurrently. Again, sorry for the short notice, but yeah. Also, I don't know. I don't know if I'm like gonna be in shape to be on campus Wednesday. We'll see how it goes. That's how you build a strong microbiome. Yes, yeah, definitely. Like eating bugs, and you know, he hasn't actually eaten any bugs, but that's because he can't walk. He can't walk, so he can't go outside, so he can't eat bugs. As soon as he has the ability to walk, we're just gonna, you know, let him loose in the backyard, and he can eat as many bugs as he likes. But for now, it's definitely the just glomping onto shopping cart handles and other such things. But yeah. Anyway, so we should probably get moving with our lecture material today, hey? I got updates. I got 99 updates, but the kernel isn't one of them. Hello from the lecture hall. Ah! Well, you know what you could do? You could, this is a thing that I'm totally not going to, tell you how to do right now, if you want to. For those of you who are joining us from the lecture hall. Avenue didn't send a notification when the announcement was posted. Uh-oh, well, maybe I can just... Maybe I can send that... Because, like, that means that there's a bunch of people... How many people are there in the lecture hall right now? I'll give you... I'll give you the, Yeah. So, edit. I will make a trivial edit and call it a major edit so that it reappears in people's things. I'll put one space in it. Update. So you should receive the announcement again about the lecture being online. 8 people. Okay, so this is what you do, okay? look up the telephone number for Classroom Audiovisual Services. It'll be on the, if you Google Audio Visual Services McMaster University, you'll get their number. Pretend to be a professor. Just say you're a professor and you'd like to use the lecture hall. They should give you the code to the projector, and then I authorize whoever's there to use that to log into the podium computer and then put my live stream up. Hey? It's that easy. Yeah. Hello to all of you 8 people in lecture today. Yeah. Anyway, so we should continue talking about our approximation algorithms. So, last time we were talking about Pythagorean triples. We kind of cut lecture a bit short. Yeah. Now I wish I was in the lecture hall, but I'm still at school. Ah, you have time. So, the Pythagorean triples, that's kind of where we left off. We left off in the middle of it. We kind of already talked about the interesting and important points, and we're in the position again where we need to start moving through this material a little faster. We talked about, like, this is a brute force algorithm, right? So the Pythagorean triples problem is to find sets of 3 numbers, which are whole numbers, which if you took them to be the side lengths, they would form a right angle triangle. So we have a couple of, we have a brute force method, then we have a couple of optimizations which we'll make, which will allow us to improve the runtime capabilities of this algorithm. Currently, we're looking at a big O n cubed algorithm, because this is a triple nested loop. I dare say the audio quality will be better today than it has been for a little while, eh? Should just bring this mic with me everywhere I go, hey? So. Yes. So this is how optimization generally works, right? When you're writing an algorithm, you will come up with probably your first impression of how to solve an algorithm is probably going to be something like a brute force algorithm. Brute force algorithms generally do more work than they need to. They enumerate all of the possibilities and then select the one that is correct. Something like that. So most of the optimizations that you will make in computer programs come from situational observations, right? So in this case, we can observe that since this is a right angle triangle, hypothetically, we don't actually have to iterate over all of the possible hypotenuse angles. We can simply we can calculate the hypotenuse from the other 2 sides using Pythagorean theorem. Now, we do lose a certain amount of flexibility here. In the original conception, it doesn't matter whether A, B, or C is the hypotenuse, these will all work, right? So essentially, we are forcing C to be the hypotenuse of the triangle, and this allows us to make this simplification yielded from the observation of the applicability of Pythagorean theorem. So when you turn that around, there are a couple of ways to do this. This one uses the binary square root algorithm that we've discussed previously in class. So essentially, C2 is a squared plus b squared. C is the binary square root of C2. So we may observe that if c is less than or equal to n, which is the original value, and if c2 is equal to c times c, then that means it's a perfect hypotenuse, right? Essentially, this is a way of checking to see if there's any fractional component that's being lost in the binary square root algorithm. Because remember, this algorithm that we discussed previously approximated the square root to the nearest, to the lowest, it sort of took the floor of the square root. So whatever the square root came up as, it was the maximum whole number that was still less than the true square root. So this is not the only way to check such things. Another way of doing this might have been to use the inbuilt square root function in Python and perform modulus 1 to see if there is any fractional component. But, you know, neither here nor there. We have, in this effect, gone from a big O n cubed algorithm to a big O n squared algorithm. How do you bring the screen down in the lecture hall? There's a little tablet device that you punched the code into. There should be buttons on there that allow you to access the screen and whether to roll it up or down. Wouldn't it be funny if we made a recording of me doing the live stream in the lecture hall, and it was just like a video recording of the live stream going on the lecture hall, and then we reposted that to YouTube? I think that would be funny. But unfortunately, the camera is right here. So, you know, that's not going to be possible unless somebody brought their own. So, again, this is because we've eliminated one nested loop, we've gone from n cubed to n squared, which is a considerable savings. So, a further observation that we can make is that when we print out all of these, we're going to get some repeated values. So the Pythagorean triples, there's kind of an implicit requirement here that, or not requirement necessarily, there's an implicit condition in this algorithm that the Pythagorean triples found by the algorithm should be unique. Now, you know, whether or not that's actually interesting to you is like another thing, right? But by clarifying and specifying these must be unique, this makes another observation about the algorithm, which we can then put to good use. So, like, for example, the difference between a 3, 4, 5 and a 4, 3, 5 triangles is sort of academic at best. So, there are a couple of ways of going about this. The first, if you were setting out with the express intention of not recording duplicate Pythagorean triples, one way that you might do that is to save all of the Pythagorean triples that you've accumulated so far in a data structure, compare any new ones to that data structure to see if they're already in there, and if they're not, put them in. If they are, then don't. But this actually will make the program less efficient rather than more efficient. In order to find whether or not any new pair is in the data structure or not, it requires a search of that data structure. Now, it doesn't matter whether you're, like, you can even use binary search for this. But, you know, because these are numerical values and you could keep them sorted. the binary search algorithm will still introduce a, log base 2n complexity to this algorithm on top of the n squared, right? So you're not you're not gaining anything. You're still losing, right? And if we used linear search, this would actually pop us right back to an n cubed algorithm. So what we can do is we can make some observations of the data itself. So one thing that we can do in order to prevent situations like this coming up, we notice if we add the additional constraint that A must always be less than B, this goes away, right? So if while counting B, we start it at A, then we can exclude all possibilities, such as this one, where A is greater than B. This eliminates all of these duplicates, and simultaneously, it means we have to search less space. So this, while this does not have an effect on the big O-ness of this algorithm, it does have an effect on the coefficient, one of the coefficients in the equation. So it will reduce your runtime without modifying the computational complexity of the algorithm. And it's just like being able to bring the computational complexity down a notch is like your golden, that's something that you really want to have. That's something that is highly desirable. But many good and useful optimizations can be made without touching the big O-ness of an algorithm. So I think I've already done a graph like this, but if we know how many steps it takes depending on the input, we can use this to predict the execution time. This can be done without knowing the details of the processor and compilation to machine language. So again, the x-axis here is the size of the input. The y-axis here might be the size of the memory usage or the amount of time required. Our goal is to get from higher algorithms to lower algorithms on this scale. As you can see, log base 2n creeps up very, very slowly in comparison to even n. So that's always our goal. So I'm just going to skip these questions because we don't have time for them, essentially. Good. So let's move right along. Just a final reminder that you should be careful with floating point representations. So let's consider the quadratic equation, which is another one that you guys should be well familiar with from your elementary school curriculum. So the quadratic formula is our two solutions to ax squared plus bx plus c is negative b plus or minus the square root of b squared minus 4ac over 2a. So you may notice in this case, if we use this equation on nominal values, then everything works out all right. If we use this equation on something containing a large value, this is no longer fine. What is in effect happening with this case in particular, our b value is negative 2 times 10 to the 8th power. When you multiply that by itself in the squared operation, you get you get 4 times 10 to the 16th power. That is large enough to gobble up this term. You remember I showed you how floating point can gobble up a term, right? So essentially what goes on here, the square operation here inflates b to the size where the gobbling will occur, and then the square root brings it back down into its normal range, so that you may not even understand that this gobbling is that's going on. You would only detect this type of error if you were doing a similar if you were verifying it by hand, right? So how do we fix this? Well, we can use decimal for exact precision, which is slower, as mentioned. We can also use an alternative formula that is more numerically stable and doesn't lead to large intermediate values. So it just so happens that the solutions of the quadratic equation are also related by a formula called Vietta's formula. x1 times x2 is equal to c over a. Given the solution with a larger absolute value, the smaller can be computed using Vietta, or avoiding the loss of significant figures. So it's tricky though, and it requires situational knowledge of the algorithm. Are there any questions about that? Because I'm just about finished with topic 6. We'll move on to topic 7. Topic 7 is kind of a short one. Give me a thumbs up in the chat. $32 is a pretty bad attendance. I suppose it's because, like, everybody's burned out from the weekend because I gave you a test. I'd kind of just like to get a survey of the class to see how long it took you guys to write the test. Please select the smallest that applies. Does that include the bonus question? Sure. I mean, how long did it take you without the bonus question? How long did the bonus question take you? "24 hours exactly." Oh, come on. My God. That's 34 votes. So, there we go. That's kind of interesting. It's like a... Spent 2 hours trying to code an edge case that didn't exist. Yep. That's not fun. Well, at any rate, useful information. So let's talk about testing and exceptions, shall we? So, this is a topic that might have been useful over the for some of you over the test, actually. You know, how to test code. So, let us consider the following program, which has a bug. Ouch, Oscar, ouch. So this function is intended to output the product of the 12 adjacent digits that have the greatest product. So, essentially, let's say you have a sequence of numbers. Numlock. Sequence of numbers, right? This algorithm finds the 12 adjacent numbers which have the highest product of any possible 12 adjacent numbers. There's a bug in here, though. Can anybody spot the bug? Preliminary results of the average for the test have come back, though, and are pretty good. Apparently the test average was like an 80, like 80.2 or something like that. So, pretty good, actually. For loop needs colon and next line should be indexed. Oh, no, that actually does work. You can inline it like that. But, yeah, it's not the form we've been doing. This isn't a syntactic bug. Product will always be greater than max product. Nope. We'll return to this. So, how can you detect bugs? There are a couple of different ways that you have bugs detected in code. In the first case, there are test cases. You run the program and you see whether or not it behaves as you expect it to. This, of course, is the manner in which your code is normally tested. You can automate this reasonably easily, which is how this is how auto grading is possible. You may have another person independently implement the function and see if both of you get the same answer. That is, compare your output to someone else's. This, of course, you can't do during a test. And have another person read your code to see if they can find any flaws. Again, in such a manner that it does not constitute academic dishonesty, please. Oh, on the subject of academic dishonesty, since it's been brought to my attention by this slide, how do I put this delicately? There's been a lot of cheating. Like, a lot of cheating. If it doesn't improve, people are going to start getting transcript notations. I'd just like to I know that the 34 people watching this probably aren't the problem, you know? There are, hopefully some of the people who watch this afterwards will get this message. At the beginning of the semester, I told y'all not to copy solutions from the internet or each other, and I specifically and particularly called out Chegg. Chegg being a well-known tutoring website, which essentially you can pay people to have your assignment written for you there, which is, just straight up academic dishonesty. So I thought that the plagiarism was pretty bad last semester. And last semester I convicted about 30% of the class. Not quite a third. A little bit less than a third of the class got an official citation from the Academic Integrity Office over plagiarism, and a fair amount of that was Chegg, but it was like a kind of a rough, even split between Chegg cases and mutual copying. The preliminary results coming back indicate that this is going to be a worse semester for academic dishonesty than last if the current trend does not improve. Like, I don't know if, like, me saying do not under any circumstances use Chegg was interpreted as I secretly wish everyone to use Chegg and copy their answers off of the internet. Like, there's just like an outrageous amount of it going on. And assignment 4, like, starting to get difficult, I guess, but, like, this course gets progressively more difficult, right? If you're crippling yourself by using someone else's answers this early on in the course, like, you don't have much hope of surviving the assignments later on in the course. If you don't have time to do an assignment, if you don't know how to do an assignment, it is better for you to take the hit and take the 0, or whatever grade you get, than to go out and cheat. We catch people who cheat, and we convict them. Alright? Do not use Chegg. Please. Like, the whole reason that you people are spending so much money on this education that you're pursuing, it's like, when you present your qualification to someone, right? I have a degree in computer science from McMaster University. What you are in fact saying is, I know stuff. I am capable of doing the work that was in this program, right? Same thing applies to the credit. It's like, oh, if you're, like, in the science faculty and you are applying to grad school and you're like, oh yeah, I got a 12 in programming in the first year programming class I took. It's like, if you cheated, it's meaningless. You don't actually know anything, and that's going to find you sooner or later. So don't cheat. Please. Please stop cheating. This is me, like, pleading with you. Listen, I know the course is difficult. I designed the course to a great degree. I know how difficult the course is. It's not difficult for no reason. What you are attempting to do is very difficult. Programming is hard. It doesn't get any easier after this class. So please just stop cheating. So, anyway, the goal of testing is to determine whether a program works as intended or not. Debugging is the process of trying to fix a program that you know already has a bug. So, the test cases reveal the existence of the bug because the test tells you, I put this in, I expected this out, and I didn't get it. Therefore, that's a bug. Not all bugs can be found by testing. Sometimes you get bugs involving what are called side effects. Like, your program may output the correct answer, but if it, like, you know, makes your printer blow up while it does, that's, you know, still bad, right? But yeah. So the term debugging is actually one that derives way back in the history of computing. Back in the days when computers were gigantic mainframes that filled entire rooms in universities. Back then, this was also before the widespread use of conductor insulation. So the wires that we work with now are all insulated, and that's fine, you know, and it's good. Back in like the 1950s and 60s, we didn't have the kinds of fancy rubber insulators on wires, and computers were there wasn't a CPU. It wasn't like all of this like green circuit board type stuff. It was people who had run wires to, you know, between relays and open contacts and vacuum tubes and all kinds of stuff. So it was basically just a huge open electric circuit, right? Every once in a while, a small animal would get into the computer. Like a mouse would get into the computer, or like a moth or something. It would electrocute itself on the open contacts and bridge circuits that aren't supposed to be bridged. Now, this would not necessarily cause the complete disruption of the machine. It might just cause an error in the logic. So the process of debugging was a computer guy, a computer nerd, opening up the side panel of the computer, crawling in while it's powered off, with a pair of tweezers, going in and inspecting the circuits to see if there are any small animals that had fried themselves, picking them out and cleaning it up, and boom, your computer works again. That's what debugging is. Give me just a second. I want to see if I got a picture of it. Yeah. So here's the world's first computer bug. So there's the first computer bug. So there you go. Very cool, right? Oh. Yeah, okay. So, these days, testing is integrated into our software development workflow. So this, roughly speaking, is how it goes. You write your program code from requirements, usually. You make sure that the compiler/interpreter can execute it. So you check for its syntactic, check to see that it compiles. Is it syntactically sound? Then you test it to determine if it works as intended. You identify the bugs from the results of the testing. This is like a diagnostic stage. You often have to dig through the code in order to do this. You then fix bugs in the source code. You make modifications to the source code, right? Then you test it again. It's very, very important to retest your code after you fix the bugs. Do never be so arrogant as to assume that your modification to the program has not made the situation worse, because you will often make the situation worse when you're trying to make it better. You must use the feedback that is given to you by objective reality to determine whether your theory about what went wrong with the code is accurate. Actually, that's pretty good life advice as well. Always use the status of objective reality to determine whether or not your theory about anything is correct or not. It's like, I theorized that I could jump off this building and not get squished on the asphalt like a pancake. It's like, well, maybe you should test that with an egg first and allow objective reality to inform you whether that's a good idea or not. So, within testing, there are two primary techniques that are used. These are broad categories of technique within which there are many different sub-techniques. So in general, you have white box testing and black box testing, although this is somewhat of a misnomer in my opinion. White box testing is much better expressed as transparent box testing. Black box would be opaque box testing. So the idea is, the stuff that you're testing is inside of a box, right? In white box testing, you open the lid of that box up and you look at it as you're poking it, right? With black box testing, the lid on that box is closed. You don't need to know anything about the source code. All you do is measure, give it particular inputs, and you measure particular outputs. Right? All we're checking to see is if the outputs are in correspondence with the known desired outputs. So, in this case, the technique that we use for auto-grading everybody's assignments and tests and what have you, that is black box technique. We do not need to look at your code in order to design the tests. This is, in fact, many people will have many different implementations of the same program. So relying on there being particular artifacts in anybody's source code is just going to result in a lot of people who wrote the assignment question correctly not getting the marks for it. So we rate your algorithms based on their objective black box performance. Both of these require a clear specification of the program's expected behavior. So, black box techniques do not rely on knowing the program's source code. They only rely on the ability to put an input in and see the corresponding output. This focuses on the development of test cases to see if the actual output matches the expected output for a given input. So, the question then becomes, how do you get the test cases? And how do you get the known output? The process for us in our the process that we use to develop the test cases for your assignments and tests and what have you is we have an instructor's solution, right? Excuse me. We run the instructor's solution with various inputs, hold on to the outputs, and use those as the model of correctness. Now, every once in a while, the instructor's solution to a problem will contain a bug in itself. However, our instructor's solutions are subjected to rigorous examination and testing by the TA team and myself, so the instance rate of bugs in the instructor's solution is reasonably low, but it does happen. When it does, we issue corrections. And, you know, so we use it as an oracle. That's another software engineering term for a piece of software that you trust to give you the correct output for given inputs, is an oracle. Now, it turns out that a lot of the time what you'll be doing, you can actually use your own code as an oracle if you're, for example, modifying the code in order to add an optimization to it, right? It's like this code should output the same thing it output before, but it should run like 3 times as fast. That type of thing. You can use the old version of the code to generate test cases for the new version, right? But yeah, it's kind of... Unless you're going to do all of the math by hand, at some point you do need, like, a good version of the code, right? And this kind of flows right into our hopefully familiar software design principles: modularity and decomposition and abstraction. So, according to modularity, a program should be broken into parts or functions that are reasonably self-contained, achieve a clear purpose, and can be reused. i.e., you should have a module. Black box testing integrates very well with modules. A module should be small enough that the test cases can be, like, visually inspected as correct, right? It's like, yes, that looks like a correct solution. If I do it by hand, it comes out correct, and I also have this program over here that generated it, which is good, right? So the smaller the module is, the better black box testing works on it, because, like, the less indirect the outputs are from the inputs, the less that has to go on in the middle. If a module gets too large, a thing that you should do with it is you should break it into submodules so that those submodules can be dealt with individually. And of course, abstraction. Once you've taken functionality and broken it into submodules, and like modules that are composed of modules and all kinds of stuff like that, all of this stuff lends itself to the principle of abstraction as well. Good. So yeah, okay. How many people have been convicted by on AD by now? Well, let's see. Convicted, we're not quite we're still, the process takes a number of weeks to get through. So we're actually, I think in terms of, like, actual hard convictions, like with letters going out, we've only got A2 done so far. And that was, like, you know, half a dozen people or so. A3 will be happening, like people are in the pipeline. In terms of, like, the number of instances that we're like sort of actively pursuing at this point, I believe it's on the order of 30-ish. And this class having 140 people in it. I think that's 1 in 8 students at the moment. Let me check. Yep. So 1 in 8 students right now. Again, I expect that number to go up because, as I learned last semester, people just simply do not learn their lesson. I guess everybody thinks I'm not the... I surely will be the person to be able to get away with it. But anyway. Yeah. Anyway, are there any questions? Give me a thumbs up if there are no questions. Cool. Okay, well, if that's the case, oh, question. For A6, there's a question that was done as an example during lecture. I'm having trouble making my code too different. Would that be an issue? Which question? Which, You mean, like, last week? I thought it was all, stuff from decimal to binary. Oh, yeah, right, no, yeah, so, yeah, that stuff, we are sufficiently intelligent in our going after people for academic dishonesty to know the difference between a question where, like, the whole class is going to come up with pretty much the same answer and, you know, a question where, you know, there's going to be a wide variety of answers. With respect to, like, the binary decimal conversion type questions, like, they're very short and all that, so you don't, like, they're not, you know, we're not going to catch you on those ones, don't worry. You have my word of honor. You're not going to get caught for plagiarism on that one unless you do something exceptionally stupid. And I don't even want to say the exceptionally stupid thing that people do, because I don't want to, like, you know, I don't, like, people already try to, like, hide the fact that they're cheating. I don't want to give them any more tells than I have to. But there are exceptionally stupid things you can do while cheating to make it, like, an open and shut case for us, you know? But yeah, those short questions in A6 about format conversion, you don't have to worry about those too much. Okay, well, if that's it, I think that's everything. I'll talk to you peeps later. I'll keep you informed and up to date as to whether or not we're going to have lecture in person this week on Wednesday. You can assume that if I'm not there for lecture, then I won't be there for office hours. Take her easy, folks.